Hello everyone and welcome to our aTech channel. Today we're going to talk to you about SpaceX's research into a new fuel for their rockets. Scientific knowledge, technical capability, and materials have allowed us to continue exploring the universe. When the first rocket to the moon took off in 1969, it is estimated that nearly a quarter of the world's population was watching the event. To achieve such a feat, researchers had to build the rocket on two stages, with the first stage running on kerosene to launch the rocket, the second stage running on liquid hydrogen to go beyond the atmosphere and reach the moon. Indeed, the powerful engines of Saturn V rocket use two distinct fuels to optimize performance. For each liter of oxygen burned by Saturn V, 0.64 liters of kerosene was needed for the first stage, while the second stage required 3.25 liters of hydrogen. For reasons like space, it was not possible to consider replacing kerosene with liquid hydrogen. Rocket science is a fascinating and complex field. It combines not only physics, chemistry, and engineering, but also logistics. This is the challenge SpaceX faces in this development. The next generation of heavy rockets is designed to take us both to the moon and to Mars. Raptor spacecraft engines will not use kerosene or liquid hydrogen. They will use methane, a fuel that has been seriously considered in research over the past century, but it has never been used on a large scale. So why is SpaceX using it now? Putting people on the moon in the 60s was one of the biggest technological challenges we've ever faced. How to reduce the cost of launches, how to produce oxygen needed for survival, how to provide water for growing and drinking, how to produce the fuel needed to return to Earth. These were all questions that were asked. Kerosene and hydrogen are not perfect. Kerosene is extracted from crude oil by fractional distillation and is composed of a mixture of long-chain hydrocarbons. The longer the hydrocarbon, the more difficult it is to burn completely in oxygen. This is because it requires more oxygen per gram of fuel to be fully oxidized. Thus, even in its refined form, kerosene often burns incompletely by breaking down into smaller reactive radicals. The result is shocking, which is the production of sodium carbon particles. These particles can easily clog the rocket's engine's complex mechanisms. This is the problem for SpaceX, as it aims to make its engines reusable with minimal maintenance, especially on Mars, where facilities to repair such problems will not be available. Liquid hydrogen does not have this problem and has the advantage of burning more efficiently than kerosene. It is possible to quantify this efficiency with a specific impulse. Specific impulse describes how efficiently a fuel can convert into a mass out of thrust. To find the average specific impulse, we must first calculate the total impulse, then divide it by the total weight of the propellant. Thus, thanks to this calculation, it was possible to define that the mixture of liquid hydrogen and liquid oxygen fuel is by far more efficient. Hydrogen has a much higher specific impulse than kerosene, about 390 seconds versus 285 seconds for kerosene. However, hydrogen is much less dense than kerosene, requiring much larger fuel tanks. Hydrogen also has exceptionally low boiling point at -250 degrees Celsius. Therefore, the tanks must be heavily insulated to prevent the explosion of liquid hydrogen. But thermodynamic equilibrium is a war of attrition that the universe will always win. So, shut-off valves must also be provided to release the hydrogen gas to prevent an explosion. All of this adds mass and complexity to the rocket. Hydrogen also degrades and weakens materials in a process called hydrogen embrittlement. This is a major problem for SpaceX's reuse project. By combining two parameters, density and specific heat of combustion, one can get an idea of the difference between these three fuels: 11.9 liters of hydrogen, 2.2 liters of kerosene, or 5.5 liters of methane. Methane is much closer to kerosene than to hydrogen, which allows methane tanks to be smaller than liquid hydrogen tanks. Nevertheless, they are not small enough to offer performance advantages over kerosene. Thus, the necessary design changes are made to be able to switch from kerosene to liquid methane, such as increasing the tank volume. Then, the increase in specific impulse is practically cancelled out. This is why methane has never been used on a large scale. Methane is simply in an awkward, indeterminate position between the most popular fuels. It offers better performance than kerosene, but not as good as hydrogen. SpaceX is working to develop its reusable rocket concept, and its interest in methane is not wanting. Methane is a single carbon hydrocarbon, so unlike the long chain molecules found in kerosene, it produces much less soot when it burns. This results in less engine damage over time. It has a higher boiling point than liquid oxygens, which allows much of the infrastructure needed to qualify using oxygen to be used for liquid methane. This is very important when working with limited infrastructure on Mars. Yet, the real reason methane suddenly became interesting to SpaceX is this. It has an enormous potential as a feedstock. To produce methane in the latest century, a chemist named Paul developed a process to convert carbon dioxide into methane. This was done by passing it through a catalyst, usually nickel with hydrogen, at high temperature and pressure. The reaction with 1 mole of carbon dioxide and reacts with 4 moles of hydrogen to produce 1 mole of methane and 2 moles of water. The combination with the electrolysis process, this produces 1 mole of methane for every 2 moles of oxygen. As a result, the mole ratio, stoichiometry, will soon become important. But the first question is, how to obtain these chemical regimens on Mars? This requires in situ use of forces. Obtaining carbon dioxide is a relatively easy task with an atmosphere composed of 95% carbon dioxide. Extracting a pure sample of the compound is quite simple. But to get rid of the remaining 5% and condense the carbon dioxide, the solution currently being considered for cryogenetics, which is the most viable option. Carbon dioxide has the highest freezing point of any gas in the atmosphere of Mars. So, in the process that is the opposite of distillation, it is possible to cool the air to separate the carbon dioxide. Then, it will freeze into a solid while the other gases remain a gas. The carbon dioxide can then simply be heated to create a high-pressure CO2 gas stream when they need to use it in their reactor. However, obtaining the hydrogen needed is much more difficult. The first option is to import it directly from Earth. But given the amount required and efficiency of storing it for long periods of time, this is not a good option. Especially because in the long term, they would like it to extract it directly on Mars. Indeed, water is contained in the Martian soil. If they could find a way to extract the water, they could convert it into oxygen and hydrogen using an electric current. Then, the hydrogen can be combined with oxygen on the one hand, and the carbon dioxide on the other, to produce methane. This process gives an excess of oxygen that can be pushed to life support systems on Mars. But extracting large amounts of water from Mars, whether from ice in the polar regions or small amounts of liquid water in the soil, would not be easy, and the technology to do it on a large scale does not exist yet. In the short term, if they bring their own hydrogen to Mars, it is possible to use the extra oxygen to use another process that would benefit from Mars' carbon dioxide-rich atmosphere. This process is similar to Paul's, and it involves the reaction of carbon dioxide with hydrogen. But instead of producing methane in water, it produces carbon monoxide in water. The water that is formed in this reaction can then be electrolyzed and the hydrogen recycled. The added benefit of this approach is that the two of the reactions, the Paul reaction and the reversal of the water-gas exchange, can be done in the same reactor, as demonstrated by Pioneer Astronautics in 2005. The combination of these two reactions has a huge thermal advantage, because the Paul reaction is exothermic, releasing heat, and the water-gas cycle reversal reaction is endothermic, absorbing heat. This results in an overall 35% reduction in heat production, improving the efficiency of the entire process. Nevertheless, research on process optimization is only a few decades old. Over the past 20 years, scientists have begun to realize the potential of carbon dioxide conversion, not least to help mitigate the effects of climate change. Instead of leaving the carbon dioxide formed by burning fossil fuels in the atmosphere, what if we could collect it and convert it back into fuel using the Paul process? This would require a method to not only efficiently capture carbon dioxide from the air, but also to create hydrogen. In December of last year, Elon Musk tweeted that SpaceX founding carbon capture and storage programs. He added that the research would be important for SpaceX's mission to Mars. It's not clear yet what exactly they're developing, but it will likely be very similar to the electro-to-gas projects that are already in development. Many people are critical of this approach to making life on Mars viable, but it's clear that this will help solve the biggest problem facing the Earth today, that of global warming due to carbon dioxide. That's it. We've reached the end of our topic today. If you enjoyed this video, leave us a little blue thumbs up. If you don't want to miss our next topic, don't hesitate to subscribe to our channel. Don't forget to turn on notifications. And thanks for sticking around until the end of our video. And we'll see you soon on aTech.